one is about kinematics, which is a branch of mechanics. Mechanics has two branches. We have kinematics and dynamics. However, we will talk about kinematics. And what is kinematics? It is considered to be a branch of mechanics which describes the motion of objects using words. You can also use diagrams, numbers, graphs, and equations without regard to the forces acting on the object. So at this point, we will not yet describe the different forces acting on the object, but we will just describe its motion. We are going to deal with an object as a particle. Let's say, for example, we are dealing with the description of the motion of a car. We will no longer consider the different dimensions of the car. We will no longer consider the, let's say, the front, tsaka yung back, as separate. But we will consider the car as one object or as only as a particle. And in kinematics also, we will be dealing with rigid bodies, wherein it is defined as a system of particles that remain at fixed distances from each other with no relative translation or rotation among them. So again, we will deal with objects which are rigid. We will not take a look at, for example, we have a clay which can actually change its shape while it's moving. We will not deal with that. We'll consider objects to be rigid. Okay, now let us differentiate distance and displacement. What is distance? What's the displacement? And how are they different from one another? Distance is considered to be a scalar quantity. That means it has no direction. It is the total path covered by the object in motion. And displacement is defined as a vector quantity. Being a vector quantity, we consider its direction. And it is the shortest distance from the initial to the final position of the object. If we are going to look at this illustration, the distance covered by the bike or by the boy here is from A to B and also from B to C. The total distance covered is equivalent to 4 meters plus 3 meters, so we have 7 meters. That is the total distance covered by the boy. But if we will consider the displacement, it is only from point A to point C, which is the shortest length from the initial position to the final position, and that is 5 meters northeast. So there's a certain angle north of east. Now, how do we describe the motion of the objects? There are different ways to describe motion of the object. What are those? We can use speeds, we can use acceleration, we can also use velocity. Now let's talk about speed. Speed is a scalar quantity, so it only has unit, it has no direction. It is also considered to be a measure of how fast an object moves. And mathematically, it is described as speed is equal to distance over time. So what is the basic unit for speed? We have, let's say, distance is expressed in meter, and then time is in seconds, so that is meters per second. So it tells us how fast object moves. What is instantaneous speed? When you are driving, then you look at the speedometer, so that is your instantaneous speed at that particular time. So instantaneous speed is defined as the speed of the object at one instant. And again, it's measured by the speedometer. At that particular point, you have this instantaneous speed, and then suddenly you change the speed from 20 kilometers per hour, then it could be 30 kilometers per hour, and so on. So that is instantaneous speed. Again, the average speed is the measure of the total distance traveled at a given period of time. So let's say in this animation we have 5 miles as the total distance covered. The car may be changing its speed as it moves from point O to the distance of 5 miles, and then it was covered for how many hours? The measure of the total distance traveled by the car over the period or the time it takes for the car to cover that particular distance. So the total distance covered here in this animation is 5 miles divided by 0.2 hours, so we have the 25 miles per hour. Velocity is a change in displacement per unit time, and the direction is very important since it's a vector quantity. So it is also used to describe the speed. However, there should be a direction. How about acceleration? When we say that the object is accelerating, what do we mean by that? Acceleration is now a change in velocity per unit time. It is also considered to be a vector quantity, therefore, it has direction. Now, how do we accelerate that object? Do we change its distance? Do we change its distance? Do we change its time? Do we change its velocity? What do you think? Okay. Ways of accelerating an object. We can change its speed. Even though, let's say, a car is moving at a linear path or in a straight path, but it's changing its speed from 20 kilometers per hour to 40 kilometers per hour to 60 kilometers per hour, the object is accelerating. More so, if it's changing its speed, at the same time it's changing its direction, it is also accelerating. But what if the car moves in circle with a speed of, let's say, 40 kilometers per hour? It has retained the speed of 40 kilometers per hour, but it's moving in circle, so it's changing its direction, therefore the car is still accelerating. Take note that in accelerating an object, we can change its speed, change its direction, or change both speed and direction. Okay, looking at the table here, you can see here, 0 second, it was 0 meters per second, so it was at rest. After 1 second, it changed to 10 meters per second. After 2 seconds, it changed to 20 meters per second. So you can see that the velocity has increased by how much? By 10 meters per second. So 10 additional 10, another additional 10. So consistently, 10 meters per second was added to the velocity per second. So that is a constant acceleration. That means same yung na-add na sa velocity niya. Or it's defined as the velocity is changing by a constant amount each second. Okay, now looking at the next examples, we have for this one we have 0, 4, 8, 12, and 16. So it's still a constant acceleration because you're adding 4 meters per second. However, in this one we have 0. After 1 second, it became 1 meter per second. After 2 seconds, it became 4 meters per second. And then after 3 seconds, it became 5 meters per second. So here 1 plus 3, and then you added 1 here. So that is non-constant acceleration. Now in our subject, we will be dealing with objects which are moving at a uniform acceleration or which are moving at a constant acceleration. Here is a mathematical description of acceleration. We have average acceleration is the change in velocity per unit time, or it's the final velocity minus the initial velocity divided by the time elapsed. When we say positive acceleration, so I want you to analyze the graphs or the table. I want you to analyze the table. Look at example A. From 0, it became 2 meters per second, then to 4 meters per second. So you can see here that the velocity is increasing. So that is a positively accelerating object. For the other example, we have from negative 8 to negative 6 meters per second, negative 4 meters per second. Still, the velocity is increasing. So again, it's positive acceleration. Negatively accelerating object. You can see here from a velocity of 8 meters per second, it became 6, then 4. So the velocity is decreasing. So that is a negative acceleration. Another example is example D, from 0 to negative 2, negative 4. So again, these are both examples of negative acceleration. Or we can say that the object is decelerating. Now we can also use diagram to describe motion of the object, since we have mentioned that vector or the using a vector, it should have direction. So let's use an arrow to represent the vector. For example, in our illustration, we have here what we observe about the length of the line here or the arrow. You can see they have uniform lengths. So that means they have constant velocity. But for this, you can see in the illustration, the length becomes longer. So therefore, it's representing velocity. The velocity also increases. So this one is accelerating. We can also use graph to describe motion of the object. Later, I will show you position versus time graph, velocity versus time, and acceleration versus time. Let's see, let's have an acceleration of 1. Say from 0, and play. I want you to observe the arrow. Okay, have you observed that the length of the arrow representing velocity is actually increasing? Now I'll show you acceleration vector. Let's start from 0 again. Let's assign an acceleration of 1 and then play. Okay, I want you to look at the green arrow representing the acceleration vector. So you can see it's not changing its length. Therefore, the acceleration is uniform, which I have assigned this one to have an acceleration of 1 meter per second squared. Okay. Now let's take a look at the graph. Let's minimize this one. Let's first have position versus time graph. But let's assign acceleration. Let's assign a velocity for the man. Let's have 2 meters per second. And then I want you to look at the graphs. Okay. Now let's take a look at this graph first, the position versus time graph. So what can I say about the graph? Okay, so it's just a linear graph, and it changes by same amount at a certain period of time. So this one, it's changing its position. Let's say from at this point, it's changing its position by the same amount at a particular period of time. After 1 second, it has changed its position with this amount, and then after 2 seconds, it has changed its position again with the same amount. So that is the graph. I'll show you later using a board how we can describe the slope of this graph. But let's take a look at the graph of its velocity. Okay, you can see here, for the graph of the velocity, you can see here that the velocity is not changing. It's just a straight line, and since we have assigned 2 meters per second in the velocity, so it's very consistent that the velocity is 2 meters per second. Is the object accelerating? No, because the velocity is not changing. We can say that the object is accelerating if the velocity is changing. Let's take a look at its acceleration graph. Okay, so acceleration graph, you can see here is 0 because we haven't assigned an acceleration. What do you think will happen to the graph of the position versus time and then the velocity versus time graph if we will assign an acceleration of, let's say, 2 meters per second squared? Can you make a guess first? Alright, let's check if your guess is correct. Now I will assign, let's reset this one. Okay, let's go back to 0. Yeah. I will assign an initial velocity of 0. but I will assign an acceleration of, let's say, 2 meters per second squared. Okay, let's check. Let's check if your guess is correct or not. Okay. Now, looking at this graph, the position versus time graph. Yan. So, we now have a parabola. If you are going to look at the slope here, okay, when we say slope, it is telling out us about the steepness of the graph. If we will draw a tangent line here, okay, I'll show you later. If we are going to draw a tangent line here, you can see that the steepness of the graph is actually increasing. Therefore, the slope is increasing. Now, let's take a look at the velocity versus time graph. Okay, you can see now it's a straight line. However, it's moving upwards. Okay, it's now increasing at the same amount per unit time also. But let's take a look at the acceleration. So the acceleration, if we are going to magnify it, there. So it's around 2 meters per second squared. It is not changing. So this one is a uniformly accelerated motion. Okay. So again, I'll show you the derivation for the slope. Okay, so let me now explain the position versus time graph, wherein position distance is here at the y-axis and then the time is on the x-axis. As I have mentioned, or in the graph earlier, we have this one, wherein it has a constant velocity. So you can see here that the slope is rise over run. So the rise is the delta d over delta t. So that is the slope of a position versus time graph. Looking at this one, so delta d over delta t is actually the velocity. So we can now say that the slope of a position versus time graph is the velocity. As you can see here, the slope is not changing. At different points, they have the same slope. That means the object may be changing its distance at a particular time. However, its velocity is constant. So this one is a constant velocity. Is it accelerating or not? So it has no acceleration. Okay, so that is the first graph for position versus time. Let's take a look at another graph. So we were also able to get a graph like this one, where it's a parabola. Okay. Now again, as I have mentioned, slope is equal to the velocity. So analyzing the slope of this graph, if we are going to look at point tangent to the graph, here, and then let's take a look at its slope. Okay, you can see here that the slope is actually getting steeper. So it's getting steeper. So that means that the slope is actually increasing. And that slope is the velocity. Therefore, this graph of a position versus time graph, velocity increases. That's how we interpret this graph, that velocity increases. Is there an acceleration? Yes. So this one is a constant acceleration. Because if you're going to get 2 points, we have again velocity is delta d over delta t. You will be able to get different velocities. Yeah. And the velocity is actually increasing. That is again for position versus time graph. Now let's take a look at velocity versus time graph. Okay, now let's take a look at velocity versus time graph. The first graph that we had is this one, wherein there is here at the y velocity, and then at the x-axis we have the time. Now let's say I have assigned a velocity of 2 meters per second. So it was 2 meters per second, and it was not changing. So it's not changing its velocity. Is it accelerating? So there's no acceleration for this one. Acceleration is equal to 0. Now let's take a look at the slope of this graph. A slope is again rise over run, or it's always a change in y over change in x. So you have delta v over delta t. It's equivalent to the acceleration. Again, the slope of a velocity versus time graph is equivalent to the acceleration. So this one, as you can see in this graph, there was no slope and there was no acceleration. For the second situation that we had a graph wherein it looks like this one. Okay, so this time we have a slope. And that slope again is the acceleration. So what can you say about the slope of this graph or the acceleration of this one? Okay, the acceleration this time is no longer 0, but it is a constant acceleration. Because if you are going to look at delta v over delta t at different points in the graph, they will be the same. So pili kayo, for example, point 2 here. Yan. At a certain period of time, delta t, delta v, and then if you're going to take a look at another slope, delta v over delta t, you will have the same acceleration, which is, that's why we have said that it's uniformly accelerated motion. If in case we had a graph, pero in the animation that we had, wala tayong ganitong graph. If in case we have this graph, what can you say about the acceleration? It's no longer constant. So this type of graph for a velocity versus time graph, it's a non-constant acceleration because as you can see, the slope is changing, therefore the acceleration is also changing. Okay, another graph that we can present is acceleration. If we have acceleration versus time here, since we are dealing with uniformly accelerated motion of the objects, what do you think will be the graph? Okay. Alright, the graph will just be a straight line. For example, this one, 2 meters per second squared. So the acceleration is constant.